I'm going to talk about lower bounds for refuting random CSPs. So basically, here is my plan, and hopefully I'm writing big enough today to be visible everywhere. I guess we are a small audience, so we can all maybe come to the the front rows in case my writing becomes smaller. Okay, so I'm going to basically explain to you the refutation problem and in some sense why you should care about it. In particular, I'll explain Feige's hypothesis, which is sort of the main reason why I think we should care about this problem. Then I'll tell you what our results are. That essentially would constitute the part 1 of the problem, part 1 of the talk, and I would take a short break. And after that, I'll basically go to the details, tell you how one could prove such a statement, and give you some pointers for some part of the proof which I think is sort of nice and clean and can be taken away, and then maybe sketch the more technical aspect of the proof. Okay. So all of you already know about constraint satisfaction, but let me just define it in all generality so that I can state the results, and also this will serve as a setting notation for what's going to come ahead. So okay, so you have a finite alphabet omega, okay, and you have some script p, which is a collection of predicates. So predicates are basically just functions that take input from omega to the k and output a 0 or 1 value. Okay, so you have collection of such functions, and in this problem the input is an instance which looks like this. So you have n variables, okay, and again these variables are the intention is that they'll take values in the alphabet omega, okay, and you have m constraints, okay, and each constraint looks like this. It's a choice of a predicate p from this set. So each constraint is a ordered pair p comma s, where p is in this set of predicates that are allowed, and s is some element of. So it's just a k-tuple of the n variables, okay, and basically what this means is that the task that you have is to find x to maximize sum over the constraints p of x restricted to the variables s, okay, where ps, so that let's say this is the set some script e, and then p comma s is in script t. Okay, so this is some extremely general way to define CSPs. Of course, you know many examples. Just so that this is not scary, let me just take the example where omega is the familiar 0 1 alphabet, and the set of predicates could be just or applied to literals, okay. So 3-bit or applied to literals, okay. So then there are 8 such predicates depending on what literal I choose for every one of the 3 variables, and for each such thing I get a predicate, and this gives us the familiar 3-sat CSP, right. And here of course x1 x2 xn will take Boolean values, right. And then so then this is just in the example this is 3-sat. Okay. Right. So in the worst case, we essentially understand everything about what happens to the question of exactly solving CSPs like this, and also approximately solving CSPs, especially if you make assumptions like the unique games conjecture, right? So there is this Schaeffer's dichotomy theorem from 78, which basically identifies all hard CSPs, all hard CSPs for exact problem. By exact problem, I mean finding an assignment that satisfies it if the instance is satisfiable here. Okay, and if you assume the unique games conjecture, then there is this paper of or let's maybe state the final paper here. So there is a number of paper, but I'll just note this because it's the last one in this series that I know, which basically gives a full characterization of approximation resistant predicates. The definition is not important. Basically, think of it as the hardest predicates. It doesn't work for larger alphabets?
The dichotomy conjecture is open.
Okay.
The
So
conjecture is still open.
okay, yes, sorry, yes. So I guess at least so yeah, that's sort of the story of the talk. Essentially, I would always think of
Schaeffer is good. I mean, the UGC thing is more.
that thing is more general, but in general, nothing would be lost for today's talk if you think of just the Boolean CSPs. Although, as Avi says, and especially for this PCP purposes and conjecture things like that, you do care about larger alphabets, especially when alphabets grow with the input size. But again, those would be only sort of peripheral concerns to us. So by and large, at least for Boolean CSPs, we essentially understand the complexity of exactly solving a CSP problem, and also essentially understand, at least if we make assumptions like this, and even without the assumption, we have a number of results that tell us what is the hardness and the complexity of approximating the CSP problem. And we will see the details, or at least in some sense ahead, but the message is that we sort of understand the versus complexity very well. And therefore, it leads us to the question, since we seem to understand the hardness, etc. of this problem very well, where are the hard instances? Like how do you construct a hard instance? And this is not just a theoretical concern, because in many applications, we are really concerned about finding a hard problem, especially in cryptography, for example, right? So all this suggests that we sort of understand what are the hard problems. But the main question that I want to ask is, where are the hard instances? And one very nice way of generating hard instances, if it works, is just to construct an instance at random. Okay. So if this kind of a method works to construct hard instances, if we can show that such an instance is hard, then it's great, because it gives us a very explicit handle on what looks like a hard seeming instance, and we can also run like simple reductions on it to basically produce hard instances for other problems, right? So which means that for at least cryptography kind of purposes, I have a great method to generate hard instances for problems, right? So so that sort of is the very basic reason why you would care about what's the complexity of, and I'll define this moment, but random is what you think it should be in this setting. But really, like, that's the reason why you should naturally care about the complexity of the random CSP problem. So when an instance is constructed at random in a natural way that I described now.
Also, the statistical physicists care about.
Yes. Yes.
Random instances.
Yes. So that's going to be my next point. Okay. So. Okay. So for choosing a CSP, this is the data, right? Like the CSP is defined by the alphabet and the predicate set. For choosing an instance, I do in some sense what is the most natural random model here, right? What I would do is pick m k tuples at random, pick P from this set of predicates at random for each k tuple. Right, and this gives me an instance with m constraints, right? Okay, so it seems like a really natural, very simple to define model, and you can ask very simple questions about it. For example, is this instance that I've created satisfiable with high probability? And if it is satisfiable, in some sense, how does it depend on how many constraints I've chosen? When can I find a satisfying assignment, and so on, right? And this, as Avi suggested before, is actually very heavily studied in statistical physics. And one of the things that they investigate is this satisfiability threshold conjecture. Okay, so basically, here's the point. If m is larger than some alpha 1 times n, so you pick some constant times n constraints, then for large enough alpha 1, just by a Chernoff plus union bound, you know that the instance is going to be far from satisfiable, right? Because you have too many constraints and only n variables. So you over constrained the system, and so such a constant should actually work, right? So here unsat with high probability. On the other hand, you know that if you pick too few constraints, then in some sense you will have an under constrained system, and you would expect to have not just one, in fact many solutions in general. So you expect that for some other alpha naught times n, you would expect the instance to be satisfiable with high probability, right? So the question is how do alpha 0 and alpha 1 behave? And the conjecture or a widely believed hypothesis, especially in statistical physics community, is that these are one and the same, that there is a sharp threshold. So basically there is an alpha which equals alpha 1 equals alpha 0, such that the property of satisfiability suffers a sharp threshold around alpha.
What you mean by sharp, but if you just want the threshold, then we know it's true. It's a Bolobash-Thomason theorem. Monotone.
So I want that so there should be some subconstant parameter, such that if I perturb this alpha by a subconstant parameter, then really.
Yeah. I mean, again, I'm not sure exactly how you parameterize. So if you want, if you increase by any epsilon away from this threshold, then you are satisfied with high probability, and otherwise
for large enough n.
For large enough, yeah.
And it should be the same.
Monotone Boolean function.
Huh.
No, but the dictator function does not have this sharp thing. You need something.
You need yeah, but I think it's simpler. So, okay, there is a general
Okay. There must be some
theorem about the mountain Boolean function way before this Friedgut and
okay, so
it's not even clear if there is a threshold, or
yeah.
clear what's the threshold.
No, yeah, both of them are unclear. At least to my knowledge, both of them are unclear. And so there must be some mismatch in the result.
Some condition that
yeah.
It's a very general theorem that applies in essentially most of this setting.
I see.
So you have it's sharp is something that is much more delicate. It depends what you call sharp. It's, you may have you may care about the subconstant change in the alpha. You may care about the rate of convergence to 1 and 0.
So I'm pretty sure like here the rate doesn't matter. So I think the threshold as they define in physics, physicists would define it as for every epsilon I should be able to pick a large enough n so that if I choose alpha minus epsilon times n constraints, then it is satisfiable with high probability, and high would be like 1 minus small o of 1. and if I choose alpha plus epsilon times n constraints, then I should be okay. So yeah, so let me assume this for now, and we can confirm this maybe in the break. So okay, so the conjecture says that there is a sharp threshold like this, and so very recently, like in 2015, Jian Ding, Alan Sly, and Nike Sun verified this for KSAT as so for large K.
Oh, you want the uniform. You want the uniform.
Yeah, for every n it has to be the same alpha.
Yeah. No, now I understand what you were talking about. No, or a fixed n.
Yeah. Yes.
So that's
Yes. So there is a sequence. Yes. There is a sequence which definitely exists.
Yeah.
It's not clear whether the sequence has a limit. So
I find it's interesting, but much less interesting than the actual threshold behavior.
yes.
The uniformity in the threshold, but anyway.
Yes, I mean I guess it's interesting in the sense that it appears true in many experiments, which is sort of it's spooky that it appears in experiments, but we haven't been able to prove it. But yeah, at least for large K, for KSAT, we have verified it now. Anyway, so assuming such a threshold exists, which at least for a fixed n it definitely does. The natural question to ask is, if alpha is less than this alpha critical, right? Then the question is, can you find an assignment efficiently? Right? And when alpha is bigger than alpha threshold, alpha critical, then the natural question is, can you certify that the instance is unsatisfiable with high probability? Okay, can you certify okay, and this is of course the important part, and then this certification question is what is called as the refutation problem, which is in the regime when alpha exceeds this alpha critical. So it appears like, even heuristically speaking, even if I don't ask for a proof, if I allow you to use your SAT solvers and run whatever algorithms you want, it turns out that it appears like even in practice this problem is hard. It's just one of those instances where it's hard not just in theory but also in practice. It appears much harder to produce a certificate that a random instance above the critical threshold is unsatisfiable. And so in particular, so as an example, the critical prediction, I was saying that they have very sharp predictions about it. So for 3SAT, the alpha critical is conjectured to be 4.27, and so you could ask for any alpha bigger than alpha critical just like this, you could ask, can I find a short proof? Can I find, okay, so does there exist a short proof which works with very high probability, and can I find it efficiently? Right? Both those questions are non-trivial, but basically, so let me maybe set a notation. So I'm going to think of m as delta times n. So this delta is what I call the density of the instance, and in some sense this would be the running parameter for us. So when delta, even when delta is n to the 49, we have no polynomial time algorithm to certify that an instance is unsatisfiable with high probability. So no polytime algorithm. Okay, and this is the phenomenon I want to investigate today. I want to understand if this threshold is inherent, and how can we sort of gain evidence for it, how can we generalize it to other CSPs, and why should we care about this problem. That sort of is the main motivation. Okay, so we go on.
You mentioned also proofs. So what is known about the size of refutation proofs?
That's a very nice question, and also because it's a very non-trivial answer. So it turns out that at delta equals n to the 0.4. Yeah, Feige and Ofek. Yeah, Feige and Ofek have a sort of very mysterious paper where they show that at delta equals to n to the 0.4, there exists a short certificate which will certify that your random 3-sat instance is unsatisfiable. But of course, we know no efficient way of finding it. Efficient methods actually work only at root n, which is a spectral method, and we are going to come to it very soon. So it's one of those situations where at least it appears here that you generally expect the complexity of NP and co-NP complete problems to be roughly aligned. You don't expect one to be easier than the other, but here somehow a proof, a short proof can be found. A short proof exists, but we don't know how to find it. Anyway, so it's a very interesting.
Between NP and co-NP, between NP and P, between co-NP and P. The ones that are finding efficiently.
Sorry. Yes. Yes. Okay. Great. So let me now sort of formally define the refutation problem and discuss Feige's hypothesis. So basically, here's what we want to understand about the refutation question. So we sort of discussed it in brief there. So there are 3 sort of parameters of our interest, and I'll basically make it clear now. So there is this density parameter. Okay. Then there is the running time. How much time does it take to find a certificate? And there is a third parameter which I also want to describe, the refutation strength. Okay. So let me tell you why, in some sense, what these parameters are and why should we care. So the way what I described there is what is known as a weak refutation algorithm. Okay. So formally speaking, what this algorithm has to do is the following. For every instance, for instance I, let's say, it has 2 options. It can either output unsatisfiable, or it has to output don't know. Okay, and we say that a weak refutation algorithm succeeds. Succeeds if probability that it outputs unsatisfiable is 1 minus small o of 1. And this is with respect to the number of variables. Okay, so with high, and this is
in a regime where delta ensures that almost surely
yes. So we are yes. So we are always going to be in the regime when alpha is bigger than this critical threshold, or even like let's say 10 times that. So we are always in a threshold where our instance is far from satisfiable. So this is definitely possible. It's not an impossible goal, but the question is there an efficient algorithm that will accomplish it for us? Okay.
Well, there is an algorithm that will always say unsat.
Great. That's why I left some space here. So whenever it outputs unsat, it has to be correct. This is what I mean by a certification algorithm. If I claim unsat, then I have to be right. I'm allowed to say don't know even for instances that could be unsatisfiable. So long as whenever I say unsatisfiable, I'm always correct. Okay, and then of course I cannot say don't know too many times. Does that make sense? Okay, and is it also clear that there is no trivial algorithm? For example, something that outputs a constant, it won't work. Okay, great. But there is a stronger variant of this refutation, which in some sense I think is nicer to study, and Feige himself makes the point about this in his paper. I'm going to come to it. This is like going ahead of myself. So I'm going to define a delta refutation, and it's basically a generalization of this. Okay, so here for any instance I define opt I as the maximum fraction of constraints that can be satisfied by any assignment. Okay? And the delta refutation problem asks you to always output a correct upper bound on opt_I. Must output a correct upper bound on opt_I. Okay, so this seems like a trivial task again. I could always say 1, but now you must answer probability that output is at most 1 minus delta for some constant delta should be as small o of 1. Okay. So and delta is this parameter in my refutation algorithm's definition here. Okay. So in particular, if delta is like 1 over m, this is just weak refutation. Okay. And in this delta, I call the strength of the refutation. Okay, great. So now, so let's sort of make use of these definitions. So the reason, one sort of main reason to care about it was given by Feiger in 2002, and this is called R 3-sat hypothesis, or at least for it. So basically, it says that for all delta positive and small enough, large enough constant c, there doesn't exist a polytime algorithm for delta refuting 3-sat. For 3-sat on m equals cn size instances. Random 3-sat on m equals cn size instances. Okay, so it's basically just makes so our current knowledge, of course, is consistent with it, and the conjecture basically says that there is no algorithmic way to improve on it, at least in this hardest regime. Oh, so one sort of nice point is that the refutation problem clearly gets easier when I increase m. I mean, this was inherent in what I talked about before, but so in some sense, like as as I increase m, I'm giving you more and more ways to find obvious contradictions in the instance. You know, if all of them are together satisfiable, then something should go wrong. If I give you more more constraints which are constructed randomly, then I'm basically making the task of finding such a contradiction easier. So as m increases, the task actually gets easier. So the hardest regime is where basically you are near this critical threshold, where you are unsatisfiable but barely so in some sense, right? So Feiger's conjecture says that for some constant c which is large enough, cn size instances are hard to refute in polynomial time. Okay, and that at least, okay, this is consistent, it also looks reasonable, but it's also extremely useful. Okay, so Feiger himself defined this, so basically he conjectured this in order to prove lots of new worst case hardness of approximation results. Okay, so there were quite a few problems, like think balanced bipartite clique, min bisection, dense SK subgraph, etc., where our hardness of approximation results based on the standard PCP machinery were actually not giving us good enough parameters. And then basically Feiger observed that if you make this assumption about random instances, that and it's sort of not hard to figure out why it should matter. It's like when you're starting from a hard worst case hard 3-sat instance, you actually have much less, or you potentially have much less structure to play with. When you have a random instance, you at least understand lots of structural properties about the instance. So in other words, you can sort of, in the reduction, you can try to make use of the properties that a random instance satisfies. And that kind of thing actually plays very well. I mean, it turns out to be very useful, and it gives you new hardness results here. Some of these were later recovered using some non-standard PCB machinery too, but still, like the simplicity of these reductions from this is, I mean, the PCB-based results which sort of recovered some of these results are much more complicated than what you get just by making this conjecture. Okay, so that's what Feige did. But later on, so this sort of relates easily. We'll see again how to hardness of refuting 3 XOR, delta refuting 3 XOR. Weak refuting 3 XOR is easy because linear equation, so I can always do Gaussian elimination. But when I go to delta refutation, it becomes a non-trivial problem. And using this again, new results were proved just by making the some sort of a similar hypothesis for 3 XOR. You get hardness for robust graph isomorphism, for example, robust GI. This is a paper of O'Donnell, Wright, Wu, and Yuanzhou from 14. Okay, and there is a candidate one-way function due to Goldreich, which can be computed in constant parallel time. Okay, if you start from this assumption, and sort of what I consider like quite an exciting result from the last 2-3 years is this new paradigm of proving hardness of learning results.
So you want to say about Goldreich that it is actually one way under the assumption.
Yes.
Yeah.
Yes. So if you assume this, yeah. So it's yeah. So by candidate I mean the candidate part is because of this assumption. Yes. And so this is application to cryptography, hardness of approximation, and the last application I want to mention here is hardness of learning. Okay. So there were like several sort of very basic problems. Some of the problems were actually mentioned in Valiant's original PAC learning paper, which were open. We didn't understand what the complexity was, like DNF learning problem. And recently this new Danieli, exactly. So this new approach due to Danieli, Shai-Shalev Schwartz, and Nati Lineal. And there are like 2 more or 3 more follow-up papers which basically produce newer results and made simpler assumptions. They began this is a really cool line of work where basically you can start from this assumption and prove hardness of improper learning, which has been an elusive goal for a long time. And they basically were able to prove super polynomial lower bounds for DNF learning problem, which was open since Valiant asked that question. Okay, so you can see it's like a powerful tool for proving new results. So that's in some sense why you should care about the validity of the hypothesis. We should try to confirm or deny or gain evidence for it. So that's the 3-sat hypothesis. But what I want to motivate is not just the 3-sat hypothesis, but also strengthenings of it. Okay, so let me tell you what kind of strengthenings I care about. Okay, so first is other predicates. Why just the sat or predicate? Again, this appears like a natural problem because it relates to the complexity of the CSP problem on random instances. But apart from that, the assumption or trying to investigate the Feige-like assumption for arbitrary predicates is useful above and beyond just the Feige's hypothesis. Okay, so let me just maybe say quickly that if you make assumption about other predicates like other arity and other predicates, then you can actually prove many more hardness of approximation results. And again, there is a lot of work here for again for this better hardness for bi-clique, densest K subgraph, okay, K routing cut, etc. Okay, and so other predicates lead to new hardness of approximation results. There is also this nice conjecture of Barak, Kellner, and Steurer from 13, which says that basically it's a trummed up RCSP hypothesis of Feige. It basically says that basic SDP is optimal for refutation of random Cn size instances. Okay, so basically it basically proposes that there is a very simple specific explicit algorithm which is just writing some simple semi-definite program, and the conjecture says that this particular algorithm, whatever guarantees it can get you, is the best possible guarantee you can get in polynomial time for the refutation problem for arbitrary CSPs. Okay, so and this conjecture was shown to have connections to, and here this is a conjecture that's made for CSPs on all alphabets, including alphabets which are growing with the input. So it has connections to sliding scale conjecture in PCP machinery, and again new hardness for densest case subgraph, things like that. Okay, so other predicates lead to new cool results. It's also there are these variants of Goldreich's candidate, different one-way functions that you can base on different CSP assumptions, and again their security depends on hardness of refuting other random CSPs.
So do we know that the basic SDP does not succeed in the refutation?
So we know that it succeeds at n to the 0.5 for 3 sat, and there is a. We know that it fails below. We know it fails at n to the 0.49, for example. Okay, these are the kind of results I'm going to state, and in some sense I'm going to prove a. Yeah, sort of. I'm going to show that such a similar, a huge SDP also doesn't help in some sense. That's going to be the main result. Okay, so I also want to say that in this Danieli paper that I mentioned, the assumptions are, at least in the first paper, the assumptions are necessarily not the SAT assumptions. In fact, Danieli did make assumptions which were about other CSPs. Some of them are actually happen to be, so some of the CSPs actually happen to be refutable using basic SDP in a clever way, which was done afterwards, like that's sort of an inspiration for our paper. But almost around that time or before that time, Danieli and Shalev Schwartz, etc., were able to just base their results on more solid assumptions, just basically 3 sat or some 3 XOR kind of variants of it, like the ones that we actually do believe are hard to refute. But anyway, like other predicates are important in this hardness of learning paradigm, especially because the predicate you use relates to the class you're proving the hardness of. So if you want to attack a certain class of learning problems, you want to say like learning some concept class is hard, then it amounts to choosing the right predicate and understand if the refutation problem for that predicate is hard. So in particular, you have to care about whether the RCSP problem on that predicate is hard or not, etc. Okay, so that's the reason I want to care about other predicates. Maybe I'll write here because this is still vague part. Okay, the second is I want to care about the strength parameter, or maybe before that, I want to care about superlinear number of constraints. Okay.
So delta is a function.
So now delta will grow with n.
In fact, for Danieli, it's essential.
Precisely. This is the point I want to make, that in many applications, it is important that delta, the assumption that you have, should actually be about growing delta with n. Okay, and for Danieli, the superpolynomial lower bounds would not hold if the delta doesn't grow with the arity of the CSP. Okay, so there you do require, so in some sense the delta there has to be n to the f of k for some f which grows with k, where k is the arity of your CSP. So that's necessary there. Similarly, in this one-way function or the related, so you can use this one-way function to come up with a PRG, and the stretch of the PRG is basically the number of constraints in your RCSP instance. So if you want superlinear stretch, you better investigate the conjecture for delta which is growing with n. So you want to care about superlinear number of constraints. You also want to care about strength of the refutation. And here it's sort of nice. So let me mention this point. So I said that when you take alpha above the critical threshold, your instance is going to be unsatisfiable with high probability. But in fact, you can say much more. You can say that for there is some constant delta naught such that if you take delta larger than delta naught, then opt-I is actually at most mu p plus small o of 1, where mu p is basically the approximation guarantee of the random assignment. Okay, so if you basically choose the assignments for your xi variables uniformly at random, and you find out how many constraints you satisfy in expectation, that's going to be this mu p, which is really easy to compute. For example, for 3 side it's 7/8, and you can prove that in general this optimum value when you take some large enough constant times n constraints is going to be actually close to this mu p, not just less than 1, it's going to be actually close to mu p, right? And therefore you could definitely, this delta refutation question makes sense. I didn't mention this before, but it's a sensible question. It's not impossible to solve. So in other words, we could potentially ask this question for delta which is like 1 minus mu p minus small o of 1, right? And this so actually there is sort of a very strong connection between the strength of the refutation lower bounds that you can obtain and hardness of approximation results. It turns out that for many of these LPs and SDP based lower bounds that we prove, like lower bounds for specific algorithms, they essentially amount to proving lower bounds for refutation, and the strength parameter here corresponds to what is the hardness of approximation ratio you get. And basically mu p is the best hardness of approximation ratio you can obtain, because it's really, there is an algorithm, the simple algorithm that returns a random assignment. Okay, and this actually clarifies this approximation resistant definition that I said before. So a predicate is said to be approximation resistant if the resulting CSP is worst case hard to approximate better than the random assignment. Okay, so one way to prove that for specific algorithms, this is a conjecture for all polynomial time algorithms. This would be a statement for all polynomial time algorithms. But to prove it for like specific LPs or SDPs, what you end up doing is basically prove a lower bound on refutation. Okay, so if you have the right strength, the maximum possible strength, then you also obtain the right integrality gap that you expect.
It doesn't matter because these proof systems are automatizable. I mean, there is a polynomial time algorithm to find.
Yes.
They are first for SDPs.
Yes.
So that's just equivalent. I mean, refutation and approximation are the same. If you are running a proof system that in which finding an optimal proof is polynomial time.
Yes, I was trying to differentiate between them because the approximation resistant question is at least syntactically about worst case problems. It so happens that our instances that we produce for proving hardness of approximation results still happen to be random.
Okay, so you are not.
Yeah, but yes, you're absolutely right that there is no difference, because in the end all these lower bounds that we prove are on automatizable proof systems, so they actually also give algorithms. Great. So so those are the three. One. So this is okay. So this hardness of approximation results is one strong motivation, but also a very recent paper of Barak and Moitra uses hardness of strong refutation, which is basically delta. So this is called strong refutation. If you get the best possible delta, it's called strong refutation. And then basically this Barak Moitra paper makes an assumption that strong refutation is basically bases a hardness of this tensor completion problem on strong refutation. Okay. So again, I don't want to go into the details here, but the point is that there are good reasons to care about the strength of the refutation parameter also. Okay. And finally, one more thing I want to care about is what happens not just in polynomial time, but super polynomial time. So far I've been talking about what can polynomial time algorithms do. But I don't want to stop there. I want to actually differentiate between quasi-polynomial time and sub-exponential time and exponential time. And this sort of relates to this general theme which has been exceedingly popular in the last few years of proving hardness results based on exponential time hypothesis. In particular, there's this recent paper of Khote and Moshkowitz which constructs a candidate Hart unique game instance. And at least the natural way to interpret the result as stated is an ETH based hardness for the unique games problem. So and their assumption is one way to sort of phrase the result, if so it's a conjecture, but the conjecture result would be that if the random the refutation problem for a certain predicate called as the Hadamard predicate is hard. So if you have some hardness for strong refutation for some super polynomial, in fact exponential time, then you can if the conjecture succeeds, then you would get a candidate hard unique game problem. Okay, so in other words, the assumption there needs to be about refuting with super polynomial time algorithms, not just polynomial time. Okay, great. So is this board supposed to be used?
If you want, I mean, later you will cover it, but you can also use it.
Maybe those two are better. Okay. Okay, great. Right. So that basically leads to my main goal today, which is basically to study the following problem for all predicate families P. Provide a strong evidence for hardness of RCSPP problem and achieve best possible trade-off between the three parameters I wrote there. So number of constraints, refutation strength delta, and running time. Okay, and the main result I'm going to show you today is the accomplishing of this goal for the sum of squares algorithm. Okay. But before I actually describe sum of squares algorithm, let me discuss this general paradigm of trying to prove lower bounds against proof systems that Avi was talking about before. So, so as I said, like this problem is naturally thought of as trying to find a proof of unsatisfiability of a certain CSP instance. So one way to study this problem, trying to prove hardness results particularly, is to basically take some restricted proof system and try to understand what's the complexity of refuting a instance in the restricted proof system. Okay. So this has been a very well explored theme. The one I want to sort of mention some results. This is Shortal Zemeredi started the study of resolution proof system for the refutation problem. Random refutation. Resolution actually Saiten. Yeah, I think Saiten began it.
I think the one for the pigeonhole principle was done by Armin Hack, not before that. I mean, yeah, so
I see. I always thought that Saiten was. I see.
Saiten did just only regular resolution. He
I see.
Problem,
I see.
Tautologies or graphs, but Armin Hack in 1980 proved the 2 to the n lower bound for the side of
I see.
Resolution of the general resolution of refutations.
I see.
And only later, a few years later,
this was for like a random.
This was for random graphs, yeah.
Yes.
Yes. Yeah,
random CSP refutation.
Random
SAT refutation. Yes. 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 So again the details are not important, but it's a particular proof system, very nicely studied proof system, and Shortal and Zemeredi in 88 showed that you require essentially exponential size proofs in this proof system. And then this was actually this was about linear size instances requiring exponential size proofs. And then you could ask, well, what happens if I have larger instances? How does the proof size vary with density? Like the kind of question we are asking today, the question was asked about resolution. And Avi and Elie Ben Sasson Yeah, so they basically answered that question completely. They had this size width relationship, and basically they used it to show the right relationship, tight relationship between density and size. And then later on, this line of work was extended to other proof systems like polynomial calculus, etc. Again, I won't go into that. Right. Sort of the one nice breakpoint that happened in this series of works is not looking for combinatorial refutations, but looking for spectral refutations, and that gave a algorithmic edge in the story. So this was first done by Gert and Krivilevich in 2001, and basically they showed that for KCSP, for KSAT, m which is larger than n to the ceiling of k over 2 is enough. Okay, so this was an upper bound, and so if you don't have the ceiling here, actually maybe just mention that result, and then later on by Friedman and Gert, they showed that for 3SAT this threshold is roughly n to the 3 by 2 plus some tiny epsilon, maybe small o of 1 for 3SAT. Okay. So in other words, the density n to the 0.5 result, the upper bound was shown by Friedman and Gert. Okay, and that's sort of what I alluded to before. Okay, and so now you could ask, I have this spectral algorithm, and I can always try to trump up the spectral algorithm by adding more constraints, writing bigger linear programs and semi-definite programs, and I can ask, well, do they help me in the refutation task, right? So okay. So this line of work was begun in this paper of Buresh Oppenheim, Galesi, Huri, Megan, and Petasi, and they basically studied this low Shriver plus SDP hierarchy, and they showed that for constant delta, I think exponential sized SDPs from this hierarchy will not help, okay, for KSAT. And as you can expect, like this led to basically a lot of results trying to understand specific SDP hierarchies, better SDP hierarchies than LSPS, etc. And the strongest one in this regime is this sum of squares hierarchy, which is also the main topic of our interest today. So let me give you like a 3-minute pitch for why you should care about the sum of squares hierarchy. In particular, why you should care about this hierarchy in relation to the random SAT problem.
We don't know that it simulates cutting planes, right?
Yeah, it's yes, you're right.
Cutting planes low bounds also, but
yes. For some kind of cutting plane methods, I think there are lower bounds. I'm not sure. Yeah.
There are exponential lower bounds for cutting plane proofs.
I see.
Let's say for Cliff tautologies, but
I see.
But they go in very different way.
Yes. So
when you say strongest, I just want to say that it's
yes. So it's in quotes, and so there is a. I think I could safely say the strongest algebraic proof complexity hierarchy that we know. Is that okay? Yeah, but in general, it's possible that there are combinatorial proof systems, propositional proof systems, which are which we don't know how to simulate in general. Okay, but at least for the random SAT problem, because spectral refutation seemed to help, it appears like the strongest method would be the sum of squares method to attack this problem.
Logical statement what you say, because spectral help that this would be the strongest. I mean, we don't know. I mean, just very strong. I think.
Yes.
Okay.
Yes.
That
Yes.
would be strongest. Very
Yes.
strong.
So let me tell you like a brief pitch for this method. So it's a hierarchy. So an algorithm in this hierarchy is indexed by a parameter d called as the degree. Applies as what we call as the basic SDP spectral methods, at least the spectral methods on natural matrices. And in general, like the reason I want to care about this today is because it has been especially successful in solving average case problems in the past few years. So for example, there are nice algorithmic results using this hierarchy for planted sparse vector, this problem of dictionary learning, and a bunch of tensor problems. Okay, so for many of these problems, it turns out that this method actually does give you new fast algorithms. So in particular, you could ask, well, does it help me in solving the refutation problem? In the worst case, it has been sort of also successful. So it captures the state-of-the-art approximation algorithm for sparsest cut. It also captures this unique games algorithm, sub-exponential algorithm for unique games that ABS came up with. And in some sense, one very strong reason to care about it in the context of CSP is this recent paper of Lee, Raghavendra, and Streuer, who showed that if you actually look at all polynomial size semi-definite programming relaxations for the CSP problem, then amongst all polynomial size SDPs, the polynomial time sum of squares algorithm is just as good. So no poly size SDP beats constant degree sum of squares. So here degree so for degree d, the running time is n to the O of d, which means that constant d corresponds to polynomial time algorithm from this hierarchy. Okay.
You showed us last time that actually this translates to super polynomial time.
For LPs.
That was only LPs.
Yeah.
We don't know that actually.
We don't know. It's a great open question. Yes. Exactly. Great. So since we believe it could be potentially useful, what do we know about the refutation problem and the sum of squares method? So what sort of appears in the first lower bound class for sum of squares all the time is this Grigoriev's proof of omega n degree lower bound for refuting K XOR, and this is on sufficiently good expanders.
So using the last results that you mentioned, the Lee, why don't you say that you're proving that no SDP can do it?
Because it wants also exponential size, not just
because you care about the size and you don't know.
Yes. So if you look at the constant time, constant degree hierarchy, then yes, the statement is accurate. But also, like the nice thing about sum of squares is that it's a specific algorithm, so you can hope to get tight trade-offs. Like at least the question seems to make sense, and we think it's sort of achievable. So that I believe is a sort of a nice way to state what's going on. For arbitrary SDPs, there are losses and all, so then it's sort of not nice to say what's the right trade-off there. Anyway, like the specific algorithm allows me to essentially solve the problem completely in a satisfying way. So I still believe that even for constant degree, the sum of squares might be nice way to state. Anyway, so and this result was sort of rediscovered by Schoenebeck, who also observed that it applies to random CSPs, random XOR, random SAT applies to random KSAT. And since then, we know a number of results like this. For example, Tulsiani extended it to higher alphabets. Okay, so one kind of result that I want to stress. Let's see. I want to erase something. Okay, I'm going to erase this part of the board. Okay, so moving on along this direction of what we know about the refutation problem in terms of the sum of squares SDP, I want to make this definition, which is an important definition to describe what's known and also sort of moving on. So it's T-wise independent CSPs, or let's say just predicates. Okay, so I say that P is T-wise independent if there exists a distribution mu supported on satisfying assignments of the predicate P such that mu is T-wise uniform. Okay, in other words, the marginal of mu on any collection of at most T variables is the uniform distribution. Okay.
Mu is supported on the ones of the predicate.
The satisfying assignments, yes. Okay. So so this definition somehow appears out of the blue right now. But Austen and Mossel basically showed a very interesting connection between this and the unique games conjecture. They showed that if you assume the unique games conjecture, then any pairwise independent CSP, so a CSP on a pairwise independent predicate, is approximation resistant. So it is the worst case analog of the strong refutation result that I was talking about, and that motivated the study of this problem. So the same kind of CSPs for random refutation. So for worst case instances, they showed that if you assume this conjecture, they are hard. And so now people wanted to investigate what happens if I take random instances which satisfy this condition on the predicates. So
Wasn't it proven also without the UGC?
no, that would be awesome to show, but we don't know how to prove this.
There is a special case.
Yes.
With,
Chan.
Chan.
Siwon Chan showed that if you have an additional algebraic condition on top of this, then the CSP, the corresponding CSP is also NP hard to approximate beyond random assignment. But in general, there can be there is a big gap, especially for sparse predicates, between the condition that Chan used and the pairwise independent condition. Okay, but it's a great problem, in fact, to show that these predicates are approximation resistant. Okay, so let's maybe move on a little bit quickly. So a paper of Ben Abbas, Georgiou, Megan, and Tulsiani from 2012 started this work of unconditional lower bounds for such predicates. So they showed that if you the omega n degree Shirali Adams, again definition is not important, it's some weaker LP hierarchy, cannot refute CN size instances, CN size random instances of any pairwise independent CSP. Okay, so they basically and this relates to what I was saying before. Even if the goal is to actually establish a worst case integrality gap, it turns out that the instances we want to look at turn out to be random instances. So even the worst case integrality gap turn out to be refutation lower bounds, at least in some parameter regimes. Okay, and again this led to a lot of results for other hierarchies. The one result I want to state, because we closely this talk closely relates to this paper, is this paper from 2015, which is the analogous result for the sum of squares hierarchy. So it's omega n degree sum of squares lower bound for refuting. Okay, so let's see. I would say random plus pruned instances of size Cn, this is a constant, of any pairwise independent CSP. Okay, so this in some sense is the strongest known result in this before this work. This is the strongest known result for any LP-SDP, Sir Adams, etc. And what basically this paper showed is that if you take exponential time algorithm for the sum of squares hierarchy, then certain instances which are not quite random, so you take a random instance and you basically throw away some sublinear fraction of the constraints, then that particular instance cannot be refuted if the CSP you started with was pairwise independent. Okay.
Yeah, by the way, you didn't give examples, but so is a good.
Yes. Yes, that's maybe I should sort of answer this thing. So XOR, the K XOR predicate is K minus 1 wise independent. And why is that? Well, because if I just take the uniform distribution on assignments that satisfy the XOR predicate, you can see that it's K minus 1 wise uniform. So that's the distribution that exhibits this property. So you can think of it as generalizing this property, generalizing 3 XOR. 3 XOR is pairwise independent, and then this is the generalization of 3 XOR for arbitrary arity predicates. Okay. Okay. Great. Okay. So so it appears like okay. So the reason I wanted to mention this is because I can point out exactly what doesn't tell us what is left to answer about the refutation problem here. So the first thing is this linear size thing. And it turns out that the way the proof worked here, it was there is a strong bottleneck to go beyond linear number of constraints, and also this pruned part, which is basically so it's not basically a refutation hardness result for random instances. It's for some pruned up instances. And those so in that sense it does give us something in along the lines of what we wanted to answer today, but only in a very restricted kind of parameter regime, even if you sort of squint away this pruning. Okay. So to summarize for this strongest proof system, the sum of squares proof system, we know some lower bounds for some class of predicates in some regime, and what we want to do today is basically fill all the gaps. Okay, we basically want to give a tight trade-off between all the 3 parameters for the refutation problem. Okay. Great. So let me state the result, and then we can take a 5-minute break. Maybe I can write on this part. Okay, so suppose P is a predicate that maps omega to the k to 0, 1. In fact, it can be a class of predicates, doesn't matter. So I want to define distance from T-wise uniformity, and it turns out that this would be the parameter that characterizes the hardness of refutation for all CSPs. Okay, so I define delta P of T as the minimum over all mu and sigma. So mu is T-wise uniform on omega to the k. Sigma is supported on P inverse 1, and you're looking at the minimum total variation distance between mu and sigma. Okay, so it's basically a robust version whatever of this T-wise independent notion that we were talking about before. We want to so for any parameter t and a fixed predicate p, I want to find out a distribution which is t-wise uniform and as close as possible to being supported on the satisfying assignments of the predicate p. Okay? Is the definition clear of distance to t-wise uniformity? Okay, so the results are going to be stated in this form in terms of this parameter. So if p is the total variation distance, mu and sigma. Sorry. Yes, statistical distance. Yes. Okay, so if p is a k-ary predicate, t is some parameter between 1 and k. Suppose I is a random instance with delta n constraints. So this then with high probability degree n over log delta to the 2 over t minus 1 degree SOS algorithm. So yeah, so this is the whole degree. Yes, that's
a minor thing.
Yeah, so you can ignore this. Yes. Sum of squares algorithm fails to okay, okay, let's see. Okay, so I will explain these parameters in a moment, but let me first point out why. Okay, so first let me just let you parse the statement. So this delta p t is the distance to t-wise uniformity of the predicate p, right? So this is the strength parameter. Okay, so you're looking at refutation at delta p of t strength. Okay, so t is some parameter that you chose. This going to be true for every t. Now you're looking at a random instance with delta n constraint. This is the density parameter, right? So you have delta density, delta p of t strength, and then you're saying that if you take a algorithm of degree n over delta to the t minus 1, then the sum of squares algorithm of that degree will fail to refute to the strength roughly delta p of t.
Something that makes sense to me. What happens if delta pt is 0, which is the case that you considered earlier, right?
Right, great. So in that case, even weak refutation would be hard.
So what do you mean fails to?
What you wanted is to output an upper bound plus 1 minus delta.
I guess I erased that. That's unfortunate. But in weak refutation, in delta refutation.
So you cannot even the output with the 1 minus lower bound.
Yes, you basically have to say 1. Okay, so does the result make sense? Okay.
So for particular, the 3 are, when t is 3.
Yeah, so when t. Yes. So that part was all okay. So if you ignore the pruned part, that was sort of already known. But the point is that now we have a full spectrum of lower bounds that hold for various densities and various strengths of refutation. And you can ask, well, what can you do better than this? It turns out that this particular trade-off is actually tight. Okay, so let me state that result.
Well,
huh?
When you say pure, just pure, or
this is the theorem I am sketching today. So this is pretty bad. I forgot to state my co-author's name, so let me correct the deficiency right now. So this is the theorem that I'm presenting today, and it's basically joint work with Ryan O'Donnell, Ruhe Mori, and David Whitmer. So David is a student at CMU, Ryan is at CMU, and Ruhe is at Tokyo Institute of Technology. Okay, and yeah, so it's not yet published, but hopefully the manuscript should be out maybe in a couple of days or so. But that's the result I'm presenting, and let me just quickly say why this is tight, and we can take a break. So the tightness basically is again due to another very fresh paper. So in fact, it's based on two papers. So there is a paper of Sarah Allen, Ryan, and David Whitmer. They are the ones who basically started looking at this problem of refuting arbitrary CSPs with sum of squares method, and they gave an algorithm extending these results for specific predicates. They gave an algorithm that basically refutes any CSP using the degree 2 SDP, and so that's this paper, and that combined with this recent work of Prasad, Satish Rao, and Salil Shram. Salil. This I get every time I say the name. Slil.
Yeah, very good.
Oh, okay. Yeah. So and this paper is extremely fresh. It's out though, and basically one way to write the results is basically, so they gave an upper bound for using higher degree sum of squares for the refutation problem, and what they show is that if you have m equals delta n size constraints, size random instance, then with high probability O tilde of n over delta to the t minus 1 degree sum of squares delta p of t minus small o of 1 refutes I. Okay, so basically precisely the parameters I stated. So this sort of completely settles there are some log factors hidden somewhere, but after those log factors, it completely settles the question of refuting random CSPs. So let me just so this statement can be a bit of a mouthful. So let me just sort of open up the parameters a little bit, and then we'll take a break. I know I've been pushing the break a little bit. Okay. So let's start off. There are three parameters, and it's getting unwieldy. So let's sort of fix one and then see what happens to the other two. Okay. So if you fix the number of constraints m to be n to the 1 plus some constant c. Okay. Let's try to understand what's this theorem telling us. Then it's like a running time versus quality of refutation or strength of refutation trade-off. So first, for constant degree sum of squares, which is polynomial time sum of squares, so this is the tight estimate. Okay, so it basically can delta p of 2 refute. So we are looking at random instance I. Okay, and now so this is about constant degree. Okay, now you can ask what happens to when I go to super constant degrees. So if I look at degree n to the 1 minus 2c, then I can do delta p of 3, n to the 1 minus c, delta p of 4, n to the 1 minus 2. I'm just computing these simple numbers. I'm doing nothing trivial, nothing non-trivial. But what I want you to observe. Okay. So if I fix the number of constraints, I'm trying to understand what this theorem is telling me about what can degree n to the 1 minus 2c SDP do. What is the strength, best strength of the refutation?
What did you write about constant degree?
It can delta p of 2 refute the instance I. Here. So
which theorem are you talking about? The upper bound result or the lower?
Both, because this is a tight estimate now. Using the lower bound is a tight estimate. Okay. So now it's basically trying to understand what does it tell us about the sum of squares SDP. So here this is a parameter, right? For every t.
Yes, we want the degree constant.
Yeah. So if I make this constant, so yeah, I'm just basically plugging in numbers here. So I'm fixing the number of constraints to n to the 1 plus c. If I take constant degree, then it turns out that I can only delta p of 2 refute the instance I. Okay. Now, so what's interesting here is this.
Refute means that the predicates you can handle are just pairwise independent.
Yes, precisely. Yes. What I want you to notice is how these numbers are actually discrete. Okay, it's not you could a priori expect that as I increase the running time slowly, somehow my strength will somehow gradually grow continuously. It doesn't. Okay, basically it goes up in this discrete intervals. You are delta p of 2 in all constant degrees, and no constant degree actually helps you beat this by a small o of 1 factors. At n to the 1 minus 2c, you rise up to delta p of 3. At n to the 1 minus c, you rise up to delta p of 4, and so on. Okay, so it basically has this discrete behavior, and we know that this is the right behavior. Okay, so that's when you fix m to be. So now let's do the other way around. Let's fix the degree of the algorithm. Since the running time is fixed now, so running time 2 to the epsilon. Then now we are trying to understand how does the strength of the refutation vary with the number of constraints, right? You can delta p of 2 refute when the number of constraints is between. Okay, so this is the n to the 1.5 regime that we're talking about for SAT. Okay, in this case you can refute with delta p of 2. For SAT, delta p of 2 is 0. Okay, because it's a pairwise independent predicate. So this basically says that you cannot even weakly refute SAT when m is less than n to the 3 by 2 minus epsilon by 2. This is what we already knew. Okay, for SAT, but this is true in general for every predicate p now. And so now, as you increase the number of constraints, your ability to refute goes up, so on. So on. Okay, and now if you especially what is especially interesting is what happens for constant degrees. So cannot delta p plus t plus small o of 1 refute I for m two, and cannot weakly refute. So that's like I can't even answer unsatisfiable or don't know correctly for m which is okay. So this is yet another definition. Okay, let me just erase this because it's not important. Okay, and basically this lead argument Stoller result from 15 says that the same trade-off actually holds for arbitrary polysize SDPs. Yes.
So basically what you're saying is that the important parameter is T. Okay, the RET doesn't matter.
Yes.
It's just what
Precisely.
Distribution it supports.
Precisely. So and
reduction, I mean, can't you reduce just to take something KRE predicate and reduce it to
that's a great question. For the purpose of refutation, essentially that's what the AOW paper invented. That's the idea of Allen, O'Donnell, and Whitmer. That so it's not approximation. It's this it's this upper bound kind of an approximation which is enough for refutation. So it turns out that for every predicate which is t-wise independent, you can construct a degree t polynomial. Even though it's a degree k polynomial, you can construct a degree t polynomial which is a good enough upper bound on it. So instead of trying to upper bound this polynomial which is naturally a degree k polynomial, the number of constraints satisfied, you upper bound the degree t polynomial, and then you pay in terms of the degree there. But that's precisely the right intuition, that t is the right parameter that characterizes the complexity, not the arity. Okay, so we'll take a 5-minute break now, and then I'll tell you more meat in the paper. So so I'm going to define this COP thing that I was trying to write before, but I skipped. So I want to call it the complexity of the predicate P, okay, and this is the parameter that is going to decide the weak refutation threshold for every predicate. So in general, I stated for delta refutation. I'm going to skip that part now, and for simplicity, I'm just going to look at weak refutation. And C of P is the minimum integer tau less than the arity and is at least 3, such that P fails to support a tau-wise uniform distribution over its satisfying assignments. Okay. In other words, look at XOR. Okay, look at 3 XOR. We said it's pairwise independent because in particular the uniform distribution over the satisfying assignments is the pairwise independent distribution. There is no, on the other hand, 3-wise independent distribution on the satisfying assignments because the 3 assignments have a linear relationship between them. Okay. So for 3 XOR, this parameter complexity would be 3. Okay. In general, like for this k XOR or k sat, the complexity is k. Okay. But in general, the complexity can be lower than k, and we want to, yeah. So this in some sense we are trying to prove a degree lower bound in terms of this complexity parameter. So the lower bound we are looking at is a degree which looks like I'm ignoring logarithmic terms now. It's like n over delta to the c of p minus 2. Okay, so let's just quickly make sense of it before I move on ahead. So look at k XOR again. For k XOR, 3 XOR again. So c of p is 3. So this is delta square, right? So it's saying that if you have a delta n size instance, then the degree required is n over delta square. Okay. In particular, if you take delta as root n, which is like n to the 1.5 size constraints, then constant degree SOS, this lower bound essentially becomes meaningless then, right? Like it says that constant degree SOS, some constant would fail, but we know some constant already succeeds. So this is like an interpolation between the constant degree algorithm which succeeds at root n, and as we said, the RRS algorithm tells you how to interpolate in between points using algorithmically, and this is the lower bound side of it. So it basically is the right answer for weak refutation. Okay, so before I move on to the technical details, let me just tell you, like in terms of the proof, the random part of the instance actually matters very little. Okay, so what actually matters is this property which I'm going to define. Yes, so it is expansion. It has to be expansion, yes, but I want to sort of state the property of expansion. I think expansion would imply these properties, but I want to state it in terms of what subgraphs are forbidden. Okay, so expansion is this nice property which is studied very commonly in this proof system. It turns out to be the one property that guarantees a hard instance. But I am going to basically describe this property as certain subgraphs being forbidden to exist in the instance that I have constructed. Okay. So okay, so let me just not write it. Okay, so that part is great. Okay. Okay, so let me do this. So for the rest of the talk, I have been doing all general things so far, but let's now restrict to a very specific situation so that the notation simplifies.
Plus or minus means that you're allowed to use both positive and negative literals.
Yes, sorry, yes, I should have clarified that. So p plus minus is the set of all predicates that you can obtain by taking all possible literals on the k variables that it depends on. Okay, so there are 2 to the k predicates. Huh?
It makes sense only on 0.
So even yeah, so right now let's say I'm only talking about Boolean. There is a version you can of course define further, but let's not go into notational difficulties. Okay.
You have like one predicate.
Yeah, one predicate, and I'm getting a set by just applying it on all possible literal patterns. Okay.
So in this doesn't strictly cover the not all equal predicate. The usual, if you're not allowing literals, like the coloring.
So the result would hold for all predicates. There is a version of the result that holds for all predicates.
Then you're not allowed to.
Yeah. So I'm stating in terms of this, but I think you can get an analogous result for even the NAE SAT predicate. Like this is some family of predicates in the end, right?
Okay.
So you can define a complexity parameter for any family of predicates, and then I think the result will continue to hold.
Even the previous results and all requires the fact that you had P plus or minus, you are needed to have positive and negative literals.
So
Or lower bound.
all previous results, yes, they require this plus or minus. So its ability to actually work with literals. Okay, so for the rest of the talk, I'm going to think of omega as just 2. In fact, omega would just be 0, 1. I'm familiar in the familiar Boolean setting. The arity k would be at least 3. So I'm going to look at 3 XOR or k XOR, things like that. Okay, and so in general, there is no restriction on every constraint being of the same arity or every constraint having the same predicate, etc. But I'm going to assume that k is the same again for notational convenience. Okay, so all arity is same. That's basically the way I've written the statement anyway. So, and I'm going to assume that this tau parameter is 3. So I'm looking at pairwise uniform things, although everything will work for anything more general things. Okay, so now I think of an instance as a factor graph. So this is the familiar bipartite graph notation for describing the instance. So this is the bipartite graph with constraints, a vertex for all constraints. So there are m constraint vertices, there are n variable vertices. Okay, and then every edge, so every constraint vertices has edges which tells which is its first variable, second variable, and kth variable, so on. Okay. So this I call the factor graph, and then since I'm looking at Boolean, so I'm going to look at a Carey Boolean predicate now. Okay, and I'm also going to have a pairwise independent distribution supported on P inverse 1. Okay, good. Let's see if I have discussed all the setup thingy. So just a notation for describing the constraints. So every constraint vertex f. So here is a constraint vertex f. I'll have a scope, meaning the variables it depends on, the tuple that it depends on. Let's call it SF, and the literal pattern on those. So I'm going to call it LF. Okay. So is the setup clear? This is just standard, but I wanted to introduce a notation before going ahead.
The usual constraints on an instance that works in resolution and polynomial calculus and the PCR and all this is simply lossless expansion or high-level.
Yeah. So here also I think.
That's it. Is that or it will be?
So for weak refutation, I think that the property I'm going to use is just expansion. I think it implies by expansion.
In fact, the degree or what would be the width of the degree would be simply the largest set which has lossless expansion.
Yes, essentially, yes. But for delta refutation, I'm not so sure that I can prove what I want by just lossless expansion. Yeah, but it's not much different. I mean, even if it's not formally by expansion, the proofs are the same. So it's not like something miraculous is going on there. Okay. Okay, great. So that's just my setup. Now let me tell you this this expansion kind of assumption that I want to make on the graph, which random graphs do satisfy. Random factor graphs would satisfy. Okay. So I want to call these plausible factor graphs. Okay, and you see the name is suggestive that they're going to happen. These are the only ones that can happen in a random instance. Okay, so to define this, I'm going to look at subgraphs of H. So let me do it this way. Subgraphs of G. These are edge-induced subgraphs, meaning that I just collect a subset of edges and then look at the subgraph defined by those edges. Okay, so edge induced. Okay, and I basically use variables of h and constraints of h with this notation. And I call the size of h as just the number of constraints in it. Okay? Great. So to define this plausibility assumption, like the expansion kind of assumption, I need a parameter to say, like, in some sense, what's the width of, so in the resolution, what's the width? And so here I'm going to define this analogous parameter. I'm call it suggestively small. Okay, that small is my parameter. And this is going to be at most n over 2. Okay. And so this relates to the degree lower bound you end up proving, or width lower bound in resolution, etc. So you should, if you want to think of it as some concrete number, you should think of it as something n to the omega of 1. Okay. And then I have a slack parameter, which you should think of as 1 over log n. Okay. So here is the plausibility assumption. So if h is a subgraph of G with all constraint vertices of degree at least 3. This is specialized for pairwise independence, where 3 would become tau whatever in general, and has C constraints, V variables, and E edges. And the number of constraints is small, so it's a small subgraph. Then so roughly you should think of it as saying that tau times C. So there is no tau, so let me just use just concrete things here. So this is roughly 3C is at least 2 times E minus V. Okay. So it can appear again out of the blue, but just to tell you why this is the usual kind of assumption that would follow from expansion. Just let's consider the case where you're looking to prove a constant degree lower bound. So m is like so m has to be close to n to the tau over 2, n to the 3 over 2, n to the 1.5 roughly, right? So then m is like n to the tau minus zeta over 2, right? So now let's try to compute the chance that in a random graph I see a subgraph of C constraints, V variables, and E edges. Okay. So I'm going to do like a quick and dirty calculation now. There are so I have to choose C of C constraint vertices, that's m to the C. Then I have to choose V variable vertices, n to the V, and then roughly each edge happens with 1 over n probability. There is some constant that depends on the size of the subgraph. Let's ignore that. Okay. So you have n to the minus E. Right. So this is the expected number of graphs of this kind that I can see. Like any particular graph of this kind, this is the number of copies I'll see, and I want that this to be much larger than 1. Right. They are the ones that would appear, or at least a constant. Let's say constant larger than 1. They are the plausible ones that appear in the random graph. Right. If it is much smaller than 1, then they won't appear. So what does this mean? It means that tau minus zeta over 2. So I'm converting everything in terms of n now, plus V minus E is at least 1. So this just is exactly what you have here, that tau minus zeta is at least 2 times E minus V. Wait.
Why you take n to the minus E?
Say it again?
Why you take n to the minus E?
M to the C.
No, n to the minus E. Why do you do
What is the probability? What do I do to construct a random graph? I have m constraint vertices, n variable vertices. For every constraint vertex, I choose the k variables in it at random from the n possible things. Yeah, so it's just like k over n to the e in general, but I'm just ignoring the k terms now. Yeah.
That's the problem.
Okay, I'm missing a few things here.
The n variables and m constraints. What is the constraint? The constraint has to pick k variables out of the n. So the probability of picking a variable, right? In order for the degree to be k, the probability of an n is k over n. That's all.
Okay. So I just did the calculation to show that this is exactly what in some sense you expect by expansion. Expansion really says that you can't have too many edges in a small subgraph. That's what expansion means in this context, and this is really so basically this is the consequence of it here. Okay, great. So just to say it concretely, so random G with density delta satisfies this plausibility assumption with small n over delta to the 2 over 1 minus zeta.
That's already taken. The tau is 3.
Tau is 3, yes. Yeah, so it's rough. It's always going to be tau minus 2 minus zeta, but here is yes. Okay, so this is the kind of instance I'm looking at, a plausible instance, which means that every subgraph that appears has a constraint degree of every constraint vertex in it has a degree at least 3, will have to satisfy this property which says that it doesn't have too many edges. Okay, great. So this is getting a little bit way out of time, so let's see. Yes. Okay. So now, okay. So you know the setup now. So let me define the sum of squares algorithm and exactly what we are looking for here in like 2 minutes. And I think many of you have already seen this. Some of you have seen this in the class. So I think I don't have to spend too much time here. So a basic object in a sum of squares algorithm is a tool to solve polynomial optimization problems. The basic feasible object, the feasible point of such a program can be thought of as a pseudo expectation, which is just a linear operator on degree at most d polynomials. So here the variables would be the x1 to xn, the Boolean variables I'm looking at. I'm going to arithmetize them and look at them as real variables. And so linear operator that satisfies the constraint that for the constant function 1 I get 1, and the important part that for every square of a degree at most d over 2 polynomial I get a non-negative value. Okay. In particular, if I don't have this degree constraint here, then this is a definition of an actual expectation. Okay, so if this is a characterization of the expectation functional associated with a actual probability distribution, so all I'm doing is restricting and basically forcing the condition that an actual expectation has to satisfy on all degree at most d over 2 polynomials. The nice thing it turns out is that I can basically search for these objects efficiently. Okay. So we say that it satisfies the constraint q equal to 0. So if there is a constraint like this, we say that tilde e satisfies such a constraint if for all p such that degree of p times q is at most d, pseudo expectation of pq is 0. Okay. Yeah, all constraints and all objectives are going to be polynomials in this program that we are looking at. Okay. So now you can ask why is my CSP problem like this? And first of all, let me just state this for completeness. So if I'm looking at a linear operator on degree d polynomials, let's look at the hypercube, right? So if I have n variables, and I'm looking at a linear operator on degree D polynomials, then it's completely specified by giving the values on degree at most D monomials. There are only n to the O of D of them. So there's any pseudo expectation can be described by giving n to the O of D parameters. Okay, so there is at least an efficient description if you don't worry about representations of real numbers. Okay, and it turns out that there is a simple semi-definite program that can optimize over this set. So it can optimize pseudo expectations of polynomials subject to these constraints. Okay, and that's called the sum of squares semi-definite program. Okay, so why is our CSP this problem? Quickly, just saying it, it's really simple. I want to find an x. I'm looking at weak refutation. So the algorithmic problem is to find an assignment that satisfies all my constraints in the CSP. So I'm going to say that for all f, PLF XSF, this is my notation for PLF being the LF shifted predicate P and then applied to the scope SF, right, has to be satisfied. Okay, so let's call this constraint 1, and then xi square equals xi. So this is the Boolean constraints for all I, right. So you agree that this polynomial optimization program is exactly what I want to solve. In general, of course, this is hard. So I'm going to look at a relaxation and look at this sum of squares version of it. So this is a polynomial optimization problem. So I can basically try to find tilde e, a pseudo distribution or pseudo expectation over the assignments such that all constraints are satisfied and my assignments look Boolean.
You actually want to prove that there is no such.
I will prove that there is such, even when there shouldn't be.
For the lower bound of the.
So basically, what I'm going to show you is that. So what I'm going to show you is that if I take a random instance with delta times n constraints for the right amount of delta, so even though it is far from satisfiable, which means there is no x satisfying these constraints, there would be a pseudo expectation of large degree that pretends as if all these constraints can be simultaneously satisfied. Okay, that's exactly what a lower bound means. Okay, great. So so let me maybe just state this theorem. So this is like a detailed version of what I stated previously. So D is this parameter 1/3 zeta small. Okay, I'm in the mood for precision today. So small is that parameter I defined at the top. Zeta is also the slack parameter I defined there, and this is the degree lower bound I'm going to prove. Okay, so there exists a degree D pseudo expectation tilde e that satisfies 1 and 2 with high probability for random instance.
Actually, you want to say that specify 1 and 2 for every instance, which is.
Yeah, actually, yes. Sorry, yeah, there is no with high probability. You're right. I want to say that. Okay, maybe 1 and 2 whenever G is plausible. So right now this kind of distinction is somewhat moot because I don't know a construction of a graph which is plausible without going through the random construction. But nonetheless, it appears like you could hope for such a construction. In that case, you won't need randomness to prove a similar result. But okay, that's a finer distinction. Okay, so that's the trade-off I want to prove. Yes, this is just a tiny parameter, it's like 1/1 log n, so you can forget about it. So really, I'm just proving a lower bound which is of the scale of small. Okay, so it's the same parameter, the width kind of parameter that we wrote down there. Okay. Okay. Great. So maybe I have 10 minutes at best. Okay. Good. So so I was going to do this planted versus random thing, but let me skip that. Okay, let me describe the sketch of the proof. Okay, so this is somehow the most interesting part, but I'm going to somewhat be fast for this part. But so the idea is this. Okay, so what do I need to do? I want to construct a pseudo expectation operator. Okay. So all proofs like this basically proceed by first guessing tilde e and showing that it satisfies some easy part of the constraints, which really correspond to showing that these constraints are satisfied. Okay, and that this constraint is satisfied, and then the rest of the proof is to show that this positivity property, right? And that in some sense is always the core technical part of all such papers. Okay, so so in general you would have to guess what pseudo expectation is, but now in some sense you have a very sort of a mechanical method in many of these random problems to actually come up with tilde e. Okay, so let me just discuss the method. I won't discuss the definition in like technical details, but let me just tell you how you could do it. Okay, so the idea is to basically define a planted version of the problem. Okay, and in many of the settings it turns out that for a random problem you always have a planted version already, sort of a very natural suggested version. Okay, so what's the planted version of the CSP problem? So a planted version is basically a problem which almost looks like a random instance, but then is completely satisfiable. Okay, so what I'm going to do is the following. I'm going to fix this graph which is plausible. So there is no randomness here. Okay, so remember that this graph is described by some bipartite things like this, right? So m vertices here, n vertices, and k scopes here, right? So what I'll do is I'll first pick a random assignment x star from +1 -1 to the n. This is my planted assignment. Then I'll do the following. What do I need to sort of construct? So an instance is described by G and the literal patterns that I use, right? So G basically describes the scopes, the SF. For every f, the SF is decided by the graph. What is not decided right now is the literal patterns. So all the randomness, all the remaining randomness is in the literal patterns. Okay, so I'm going to choose the literal patterns so as to make x star a satisfying assignment. Okay, so the way I'm going to do this is following. I'm going to choose x star uniformly at random from +1 -1 to the n. Then I'm going to, for every constraint f, I have this distribution mu, right? The mu, which is a pairwise independent distribution supported on satisfying assignments of the predicate. So I'll sample a z, let's say zf, from mu. Okay, and then at any, so now I have to decide what's the literal pattern I want to give to the ith. So let's call this 1, 2, and in general I. The ith variable of the constraint vertex f. I have to tell you what literal I should use there, and I'm going to use the literal LFI equals ZFI times, so it's in +1 -1 world, I'm XORing, so it will multiply here, times x star I. Okay, and essentially I have done nothing. Basically, if mu is the distribution supported on the satisfying assignments of P, then mu XORed with LF, the literal pattern, is a distribution supported on the satisfying assignments of P on the literal pattern LF. Okay, so this is a shifted version. So I just basically ensured that the shifts I use agree with, so the distribution basically I'm inducing is the right distribution here, supported on satisfying assignments of the shifted predicate. Okay, so now this instance is going to be satisfiable if I do this, right? But you still sort of see that it looks pretty much like random, at least because I mean clearly there is much fewer bits of randomness here. I just have chosen x star and z, but it's still, you could think that, or at least you could very well define the problem of distinguishing between this instance and a completely random instance. Okay, and the intuition is that not just that the instance here looks satisfiable to the algorithm. In fact, it looks like a planted instance. Okay, so it looks like an instance where I basically did this to generate it. Okay, so my pseudo expectation wants to pretend like this, and in fact it can pretend consistently. That's the point. Okay, so basically what you can do is this recipe gives you a black box method to write down what pseudo expectation you should use. Just once I define the planet problem, everything is basically settled. Okay, the truncation, etc. Okay, there is some technical detail, but everything else is sort of settled. And now what is left to show is that that your pseudo expectation satisfies the constraints. The tilde e1 equals 1, and these two constraints that I wrote down here. Okay, so it turns out that all of the other things, the constraints part is always simple when you go through this planted versus random methodology. Okay, and now the proof of positive semi-definiteness is always sort of the meat, as I said before. So here we proceed in 2 steps. Okay.
But previously, if I don't know about your paper with Bharat, the Tulsiani one, they didn't show there the pseudo expectations did show as if they were the pseudo expectations coming from a planted instance.
They didn't write it that way, but the operator we construct is the same.
Oh, okay.
So yeah, that's I mean depending on how you see it, it could be miraculous, or in some sense it says that really there is only one thing to work with here. If you do
as an implicit planted instance
Yes, yes, yes. So in fact, I'll tell you in a moment what it corresponds to, just like in 1 minute. So the proof here proceeds in 2 steps. Okay, the step 1 is the easy step and is to reprove the BGMT kind of result, to show a Sherali-Adams lower bound, which means to show the following: for all polynomials p that depend on at most d variables and non-negative, I want to prove that this is true. Okay, so this is the I call it the local PSDNS property. So low degree polynomials are not generally local. They depend on all variables in potentially. But suppose I had a polynomial which depends on at most d variables, d being the degree that I'm shooting for here. Then I want to first argue that tilde e is always going to be non-negative if p is non-negative.
You don't even care about square.
Yeah, here I don't even care about square. Precisely, yes. So this is, and this basically, this step, it corresponds to showing a Sherali-Adams lower bound. Okay, and this part basically, so this is equivalent to saying that on any collection of capital D variables, my pseudo expectation is an actual expectation corresponding to some local probability distribution. So it's an actual distribution such that my pseudo expectation, when marginalized over these d variables, agrees with the expectation of this local distribution. Okay, so you basically argue that there is a local distribution, and it's a very natural local distribution. Let me just say it out loud because it requires proof, and I was going to do it. I can't. So the local distribution is just this. Okay, you look at so if you look at any so suppose I'm looking at some set of variables s which is of size equal to capital D. Okay, so I define all plausible subgraphs. So take all plausible subgraphs of G with constraint degrees 3. So every constraint vertex has to have degree at least 3. Take all such subgraphs, take their union. Okay, take union of all these subgraphs. So it's some collection of variables and some collection of edges in my factor graph. Okay, it turns out that this is easy to show that this graph cannot be large. In fact, its size is going to be small. Small being this parameter that we're thinking about. Okay, so it's going to be a small subgraph. Okay, because, and the reason is that it has to be plausible, and then you know that okay, so we sort of it just follows from the assumption we made. So nice thing is now that you can basically define a local probability distribution on this small subgraph, and is essentially some kind of a conditioning of the planted distribution. Okay, so if you look at the planted distribution and condition it and marginalize it over this set, it turns out that the distribution you obtain is the local distribution. Okay, so both of these kind of things can be interpreted as saying the following. It basically says that the pseudo expectation, okay, pseudo expectation of any monomial chi s of size at most d, even though it has this global constraint where it says that every degree d polynomial square should be non-negative, actually is a very local function. Okay, so this basically corresponds to, I mean, I'm not explaining why this is true, but it basically corresponds to saying that is a local function. Okay, so it depends only on some small subgraph that contains S. Okay, so now it turns out that since there is a local distribution there, it's easy to show that this step 1 is true. Now you want to go from step 1 to step 2, and that's sort of the hard step. Okay, and now I'm going to do just 2 minutes of this, and in some sense this is where the real stuff happens in the proof. So you want to somehow piggyback on this local PSDNS and prove global PSDNS. So what you
have you defined the pseudo distribution already or not yet?
the pseudo distribution is defined just when I do this planted versus random thing. From there it's fixed. I haven't told you that, and I think I won't have time to tell you that. Okay, but it basically.
If you ask him in the question.
But yeah, if you ask me in the question, I can tell you. Just let me just finish off, and then we can do that. So for step, so it's some natural pseudo distribution that you come up with by doing this planted versus random methodology. Okay, the step 1 part is also simple in that you can prove local PSDness. For going from local PSDness to global PSDness, one natural idea is to basically invent a basis, invent a new basis of degree d polynomials. Let's say chi 1 tilde, chi 2 tilde, so on up to chi m tilde, such that this basis is orthogonal. Okay, so you want to say that with respect to tilde e. Okay, if I invent such a basis, I am of course done, right? If I can show that there is a basis of degree d polynomials which looks like this, then I am done. Okay, why? Because if I look at any polynomial, I expand it in this basis. When I square it, I am basically trying to compute the pseudo expectation, which by linearity I can push inside. Pi times pj times chi I tilde times chi j tilde. The cross terms vanish because of this condition, and the square terms are non-negative because I get a pi square. Okay, so the reason how do I come up with this basis is the question. One thing is to just do Gram-Schmidt, right? If I knew that this pseudo expectation was PSD, I could do Gram-Schmidt, right? But now it seems somewhat silly to do it because it's sort of equivalent to proving its PSDness. So what we end up doing is we do a Gram-Schmidt syntactically with respect to this linear operator. The orthogonality is a syntactic property of Gram-Schmidt. It works for all linear operators. It doesn't care about PSDness. What is non-trivial is getting this non-negativity property. Okay, so what we show is that after you do Gram-Schmidt, even though it's highly sequential and you could potentially depend on all possible monomials, what we actually show is that every new basis function that you define actually is still a function of small number of variables.
The same small like.
Yes. Yes.
So it's a local process. So it's
yes.
all similar, very similar to all the other proof.
Yes.
For other proof systems.
Yes, yes. At a high level, I think the proofs all. I think in some sense, all these proofs are saying about these random CSPs is that all efficient algorithms seem to just look at the instance locally, and locally all these instances look very highly satisfiable, and they are basically not able to get any global information about the instance. So they are so they're computing things which are garbage. So this is like this is a recipe for computing what garbage sum of squares can compute. Okay, so I'll stop here and then answer questions.